So for lecture 6, we're following a similar progression like we did with axial deformation, where we did axial deformation and then we did statically indeterminate axial loads. So last lecture we did our first lecture looking at shear stress caused by torques and angle of twist associated with that, and now we're doing statically indeterminate torqued members. So today's lecture is going to be a pretty short one. Seeing as you already have a little bit of a grounding in compatibility criteria and dealing with things that are statically indeterminate. So let's look at the example of having an object, a rod, let's say. Here's one end and here's the other end out there. There it is. Okay. And this end's fixed to a wall, and so is this end. Right? Both ends are fixed. And we've got an applied torque T here. And this end is, let's say, A, and this end is B. And what we want to do is find support reactions. So for our equations of statics, if we change this into a free body diagram now, we'd know there'd be some opposing torque on the wall at this side, TA, and some opposing torque on the wall at this side, TB. And logic and experience would tell us that because that applied torque is closer to point B, then TB is going to be greater than TA, and indeed that's the case. And we'll see how the mathematics of that shake out. So from the equations of statics, though, all we can say is that if this object is static, then some of the, let me get my pen working here, some of the torques has to be equal to 0, which means that T has to be equal to the summation of TA plus TB, right? If we had a value of T, then we'd have one equation and two unknowns. So we've got one equation from statics and unknowns of TA and TB if indeed we know the value of T. So again, does that mean that we're stuck? We can't find TA and TB? Well, no, because we know something about the deformation of this object. We know that because end A is fixed on a wall and end B is fixed on a wall, then the relative angle of twist between those two ends is 0. So we know that angle of twist phi from A to B has to be equal to 0. Now that doesn't mean that the rod doesn't twist in between A and B. It just means that whatever twist occurs from A to, let's say, the point where the torque is applied, point C, is undone by a twist in the other direction from C to B, so that the total angle of twist is 0. So again, if we wanted to take this equation for angle of twist and apply it, we'd have to use superposition here, because we can see that in this section of the rod, we're going to have an internal torque TAC, and that internal torque is going to be equal to TA. But in this section of the rod, we're going to have an internal torque TCB, and that internal torque is going to be equal to TB. So different internal torques means that we have to split up the rod into two segments when we apply our equation for angle of twist. So we have to say that phi AC plus phi CB is going to be equal to 0. And then we can expand those out using our equation for angle of twist. So phi AC is the torque in AC, LAC divided by J and G, and I'm just leaving the subscripts off those since both segments have the same J and G, but of course you couldn't do that if one portion was smaller or larger than the other portion, or if they were different materials. TCB LCB divided by JG equals 0, right? So we can cancel out our J's and G's, and then we sub in for TA sub in TA for TAC and sub in TB for TCB, and then all of a sudden we've got our second equation. And two equations, two unknowns, then we can solve that. So without going through any more of that, because I think you get the idea, let's do an example problem and stick some numbers to it. Okay, example. So what do we have for our example here? So we're going to have sort of a similar looking picture, but a little bit different. And we'll have that there, and then okay, so you can probably see what's going to happen here. We've got this portion of the rod here that is going to get smaller and have a smaller diameter portion that is fixed to the larger diameter portion. So maybe this is a single piece that has a change in diameter and it's being machined that way, or maybe it's two pieces that have been welded together. In any case, they're both fixed solidly together, and we've got a diameter on this piece, the larger portion of 2 inches, and the smaller portion has a diameter of 7/8 of an inch. And then we're going to have a torque applied to this, and that torque is going to be right about, let's say, there. And its value is going to be 1150 pound-feet. Foot-pounds, pound-feet, whichever way you please. And distances here, 16 inches. And another 10 inches, and then this small diameter portion is going to be 8 inches. Obviously, not drawn perfectly to scale here. Okay, and importantly, both sides of this rod are going to be fixed to walls or rigid supports. So our question is, the rod is, the whole thing's made of 6061 T6 aluminum, and what we want to do is simply find the maximum shear stress in the object. So rod made of 6061 T6 aluminum, AL, determine tau max. Okay, easy. So in order to determine the maximum internal shear stress, we need the internal torques. Now, because we've got two different diameter regions, it's not immediately apparent whether or not the largest shear stress is going to be in the small diameter portion or the large diameter portion. So we'll probably end up having to calculate shear stresses in two locations and compare them. But first and foremost, we need what those internal torques are. So let's put some labels on our drawing here. So let's make this side A over here and this side B over here, and then we'll put our intermediate points. So where this torque's being applied is point C, and then where the change in diameter occurs, let's make that point D. And then let's draw our free body, or change this into a free body diagram here. So we'll erase the supports like this. Okay, do some nice careful erasing there. And we've got the wall is going to produce a counteracting torque to the applied torque, and so will the wall on this side. So we've got TA and TB. So our equation for statics, so we've got sum of the torques has to be equal to 0 for this. And we've got the summation of TA plus TB then has to be equal to 1150. Now change this into pound inches from pound feet. Remember, when you're working in US units, you want everything in pounds, inches, PSI. So we're going to multiply this by 12 to change it to pound inches. So we've got one equation there. All right. For our second equation, we're going to need to consider deformations for compatibility criteria. So we know, what do we know? We know that the angle of twist from A to B has to be equal to 0 because both A and B are fixed. And because of superposition, we need to break this up into component segments. So maybe it's confusing if I write it that way. So I'll write it on a new line. So we've got, or no, let's keep going that way, and that gives us a little bit more room. So we've got angle of twist AB is going to be equal to the angle of twist from A to C, right? That's going to have one internal torque in it, and then as soon as we cross over from point C to the other side, then the internal torque will change. So we need a segment from C to D, and then even though the internal torque between C and D will be the same as D and B, the diameter changes, so we need another segment to take us from D to B, right? So anywhere where the internal torque or the cross-section or the material changes, you need to break it up into segments. Okay, so now all we do is expand this out using our equation for angle of twist. So we've got us for segment AC, the torque in AC, the length of AC divided by the J value for AC, radius of gyration, modulus of rigidity, and I won't put a subscript on G because the whole thing's 6061 T6 aluminum. Internal torque in CD, length of CD, over the J value for CD and G, plus internal torque in DB, length of DB, over radius of gyration for DB and G. Okay, and all of our G's there disappear because we've got a 0 on the other side of that equation. Okay, so if we can stick some numbers in there, then we could potentially have two equations and two unknowns. So let's continue. What makes sense to do? The lengths are all easy. J values are all easy. Internal torques. Let's get our internal torques. So for the internal torque in segment AC, actually I'm going to copy this and bring it over to our new page so we can look at the internal torques while looking at this, and we can draw all of our internal torques on a single page. So let's paste that there. Okay, good. And now we'll do our section cut between AC. Okay, so for that free body diagram, we've got something that looks like this. Now, really important to get the directions of your arrows correct here. If we've drawn TA in the direction that it's shown above here, right there, we want to draw it in the same direction when we take the section cut through the object. That's very important. So we've got TA like this. Now the counteracting torque has to be in the opposite direction. So we've got TAC there. And sum of the torques is equal to 0. TAC has to be equal to TA. So our next location, we cut in between C and D there. So our free body diagram for that section cut. Okay, there we go. And we've got what? We've got TA in this direction, and we've got our 1150 pound-feet in that direction. Now, unlike the previous section cut, it's not at all apparent what direction the internal torque is going to be in here. So just make a guess, and the math will take care of it. So let's just put it in the same direction as the 1150. Okay, so there we go. So this is going to be the internal torque in CD. Okay. Now our equation of statics for that segment there, we have sum of the torques is equal to 0. So we have the 1150, and we're going to change that to pound inches again by multiplying by 12, plus TCD is equal to TA in the other direction. So TCD is equal to TA minus 1150 times 12. Okay, so we've got an expression for the internal torque TCD in terms of our support reaction torque TA, so that's good. And then over here we had TAC equals TA. Now we could take one last section cut between D and B, but we don't really need to do that because we know that the internal torque between D and B is the same as the internal torque in between C and B, or C and D, because there's no internal torque being applied anywhere, or no external torque being applied anywhere between points C and B. So for example, our free body diagram, if we were to section cut between B and D, would look exactly the same as if we extended that section cut and did it between between points C and D. We know that TDB is equal to TCD is equal to TA minus 1150 multiplied by 12. Okay, so let's go ahead and fill in some numbers in our equation. So let's flip back here, and we'll steal our equation from over here that we had. Okay, copy that. Flip it to the next page, paste. Okay, remind ourselves that this was a 0 on the other side there. Okay, so let's start filling it in. So we've got TAC. So remember, when you're filling in these internal torques, you need to be using the right-hand rule to figure out whether they're positive or negative. So you look at your section cut and orient your thumb so it's pointing out of that section cut, and then your fingers of your right hand curl in the direction of a positive internal torque. Now, TAC is going in the opposite direction, so that means it has to go in as a negative. So instead of putting TA in the equation, we have to put negative TA in our equation there. So we've got minus TA, and then the length of segment AC, which was 16 inches. So we've got 16 in here divided by j, pi over 2. Radius to the 4th power. Diameter was 2 inches, so our radius is 1 to the 4th. Plus TCD. Let's flip back here. So again, your thumb, look at the section cut. Where's the red? There's the red. So look at the section cut, point your thumb out of the section cut like that. Fingers curl in the direction of a positive internal torque. That's in the opposite direction of TCD. So TCD needs to go in the equation as negative. So this whole expression here needs to go in as a negative value. So we've got TA minus 1150 times 12. So minus TA minus 1150 times 12. Okay, another bracket. And then LCD is just the length of segment CD. That's 10 inches there. So we've got 10. Then divide through, and our J value is exactly the same there because we're still in the larger diameter portion. And then we hit the smaller diameter portion. Now, we know that the internal torque in the smaller and larger diameter portions are the same there, so we can just pop in that exact same expression, minus TA minus 1150 times 12 multiplied by the length of that smaller segment, which is 8 inches, divided by pi over 2 multiplied by, what did we have for the diameter? The diameter was 7/8, so the radius is 7/16. So we've got 7 divided by 16 to the 4th power. Okay, and that equals 0. All right, so second equation. So now, flipping back, we have our equation of statics, right, which gave us one equation, and our equation for angle of twist based on our compatibility criteria, that there can be no angle of twist from A to B. That gives us our second equation, so we can go solving 1 and 2. We get TA and TB. Okay, so doing the math on that, we get TA is 12,896. Okay, 12,896. And remember, we converted things to inches here, so this is coming out in pound inches. And then for the torque TB, the support reaction torque TB, we've got 904 pound inches there. All right. So now we were asked for what the maximum stress was. So let's have a look back here. We know that the stress in this segment, hope I'm drawing so you can see, the stress in this segment right here, TDB, and let's do that in blue actually so you can see. So we know the stress in this segment right here, TDB, is equal to 904 pound inches. Okay. And that's going to be the same stress as we see in this location between D and C. Now, the radius goes up, or the diameter goes up significantly between BD and DC, but the internal torque doesn't change. So we know for sure that the stress in segment CD is going to be lower than the stress in segment DB. So we definitely don't need to check what the stress is in segment DC. But for segment AC, it's got a larger diameter than segment DB, but the internal torque is also significantly higher. So we've got an internal torque in that segment of 12,896. So TAC, we've got 12,896 pound inches. Okay. So in this section here, high internal torque, larger diameter. In this section here, lower internal torque, but smaller diameter. Not clear which is going to have the maximum shear stress, so we need to check both. So let's do segment AC first. Okay, so for AC, so we've got the shear stress. The maximum shear stress in segment AC will be equal to the internal torque in that section multiplied by the radius of that section divided by the J value for that section. Again, we're using R here instead of the variable rho because we know that the maximum shear stress due to a torque occurs at the circumference where rho is equal to R. We've got 12,896 multiplied by a radius of 1 inch divided by pi over 2 radius to the 4th power. And that gives us 8.2 KSI. Okay, so now let's check the smaller segments. So that's for dB. For dB, got the shear stress in dB, where the maximum shear stress in dB is the torque in dB, the radius of that segment, and the radius of gyration for that segment too. So we said 904 pound inches multiplied by a radius of 7/16 divided by pi over 2 7/16 to the 4th power. That's giving us 6.9 KSI. Okay, so indeed the largest or the maximum shear stress occurs in segment AC, and it's 8.2 KSI. So we've got therefore tau max equals the maximum shear stress in AC equals 8.2 KSI. Okay, so there's that example problem done. So that's how you do or how you handle statically indeterminate torque-loaded members. Okay, so one couple of minor topics to take you through, and we'll flip to the textbook for a moment here. Let's flip a few pages ahead. So here's statically indeterminate torque-loaded members. Just like for axial deformation or for things that were axially loaded, we can also get torsional stress concentrations too, anytime we have something that has a change in diameter. So a shaft that's going from a large diameter to a small diameter, there'll be a stress concentration there. And we go about doing or handling those in exactly the same way as we did for normal stress due to a normal force. You simply calculate what your maximum shear stress would have been ignoring the stress concentration, and then multiply by a stress concentration factor K, which you get from a table like this one here. And again, the value of K is read off the y-axis and depends only on the geometry of the object that you're dealing with. So we're not going to deal with stress concentrations in torsion in any of our problems. And again, this is more of a concern if you're dealing with a brittle material than a ductile material, because in a ductile material, if there's a small localized region that experiences a stress concentration and goes over the yield stress, then we're just going to get a bit of plastic deformation and strain hardening, and there won't be any failure of our component. So stress concentrations happen, again, anytime you have a change in diameter. So that could be due to a situation where you have two shafts being joined together by a coupling, or, for example, a pulley held onto a shaft by a keyway like this. So any of those things will cause stress concentrations, but we're not going to deal with them. All right, so the one other thing to take you through is torsion of non-circular shafts. So you'll remember that when we were deriving the equation T rho over J, we built that equation up by considering something that was circular in cross-section. We had our little volume or little element of material dA there, and we were doing an integration around the area, and we split that up into a double integral, one in the radial direction and one in the circumferential direction, where we integrated from 0 to 2 pi. Because we did that double integral in the way we did to cover the full area of that cross-section, the result is that this equation that we developed is only valid for things that have a circular cross-section. Okay, so it's only for circular cross-section. And I know formula derivations are sometimes hard to sit through, but they do tell you a lot about what a formula can and can't be used for. So for instance, in this case, we know that can only be used for a circular cross-section because that was built into the derivation of it. and it doesn't apply to things with rectangular cross sections or triangular cross sections. We don't often see those being loaded with torques, but sometimes they do occur. And it's important to realize that the way shear stress varies with circumferential or with radial distance from the center of a shaft is quite different in something that's a square cross section versus a circular cross section. So for something that is circular in cross section, if it's subjected to an internal torque Ti, then we know what the profile of shear stress is going to be at any radial location. So we can take any radial line that we want here and know that the shear stress will be maximum at the outside or the circumference and then decrease linearly moving towards the center. So that's our distribution of shear stress over the cross section. And again, we can do that on any radial line we want. So we could take a radial line there, for example, and the shear stress at the circumference would be the maximum shear stress that is felt in the rod, and it would be oriented at an angle that's perpendicular to that radial line or tangent to the circumference, up like this, and then a linear decrease moving towards the center, zero shear stress in the center. So we have tau max at the circumference decreasing to zero in the inside. Now, if you look at something that's got a square cross section, for example, the situation is quite different. If this is subjected to an internal torque, then you might be tempted to think that the farther you can go from the center, the higher the shear stress will be. So the point that's obviously, or the points that are farthest from the center are the corner points. But as it turns out, the shear stress is actually zero at those points. So the distribution of shear stress along a line like this actually varies something like that for something that is rectangular. And the maximum shear stress actually occurs along a radial line going out to the center of the side of the object. Now, the interesting question is, why is the shear stress zero there? And you can assess that by looking at a very small element of material located at that location. So if we draw what's called a volumetric element of material that's located at that position, here we go. So we've got our element of material, and let's put in the sides there and another side there. So let's say our shear stress is oriented in this direction here, right? So we're going to break it up into two components, one that is a vertical component here and one that's a horizontal component, like that. Okay. So if we look at the consequences of those shear stresses, let's just deal with one of them, and the other one's, the situation's exactly the same. So let's just look at that vertical shear stress here. So I'm going to erase the other ones. So this is shear stress tau, and it's acting on area dA. And this is a cube of material, so all of the sides have the same area. And we know what the product of tau dA gives us. It gives us a force. So taking some directions here and saying that this is, let's say, X, Y, Z. So now we've got a force in the positive Z direction acting on this little element of material, which means that it's not balanced in static equilibrium. We need an equal and opposite force acting downwards. So how we need to get that force would be by having an equal and opposite shear stress acting on the back face. But now this cube of material is not balanced in terms of the torques that are acting on it. It's got a force couple that's acting on it, so it is going to want to spin around the y-axis in that direction. So we need something to prevent that. So what we need is a shear stress acting on the top there, again multiplied by area dA gives us a force, and then now the forces in the x direction aren't balanced, so we need an equal and opposite shear stress on the bottom, tau. There. So only now are the shear stresses actually balanced, and so only now are the forces on this element of material actually balanced, and it will remain in static equilibrium. So this happens whenever you have shear stress. Whenever you have shear stress in one direction at a point or on an element of material, you have shear stresses in 3 other directions. And those are called complementary shear stresses, and they're required for static equilibrium. The problem here is that the top of this object is just touching air, so there's nothing that can apply a stress there. So on our element, it's this top side that's touching air, and because that's touching air, it means that this shear stress here can't exist because there's nothing to apply it. And if that shear stress there can't exist, neither can that one. And if those two can't exist, neither can these ones. So because of the requirements for static equilibrium, that's actually why that point up in the corner there cannot support any stress. So just an interesting idea for you to think about and appreciate. And we'll see this sort of analysis where we look at stresses on a volumetric element come up a lot more as we move through the lectures on combined loading and looking at adding stresses due to multiple different internal forces. If you do ever need to calculate shear stress for objects of non-circular cross-section, there's specialized formulas for those, so they'll be available in any good engineering handbook. All right, so that brings us to the end of Lecture 6. I'll see you again for Lecture 7.